Okay, let's begin. Homework number 4 is available now, and it's only 2 problems long. And your last assignment was only 2 problems long as well, right?
Is this a future trend we're going to have?
I don't know.
I like it.
You like it?
I like it.
Okay, I guess I could make multi-part problems and then just combine it so that there's only 2. But in this case, yeah, 2 problems. It's due on Wednesday the 12th, and the entire assignment just covers material we're covering today in class. And so you're not going to have to wait until Friday or Monday to get the rest of the story before you begin on it. I'd encourage you to get an early start because the second problem in particular gives students trouble. It conceptually is a little bit confusing, and I'll maybe give you some some hints in a future class, but please at least look at it after today's class just so you can get an idea of what it's going to entail. So it's available now. I wanted to address that I'm not going to post solutions to the homework assignments and why I've made that decision. I think in fluid mechanics last semester I did post the homework solutions online. Is that right? Do I remember correctly? So I'm not doing it this semester because what I realized is the whole reason I'm writing homework problems is that in past semesters when it was from the textbook, sometimes students were finding solutions online and then just relying on those rather than solving the problems themselves. And so I'm writing questions because I know there's no solution out there because I just invented the question. And if I post a solution, then next year that solution might find its way to some of the students who take the course next year. And so I just want to cut back on any opportunity for relying on an existing solution versus having to do it yourself. So that's why I'm not posting the solution. And I recognize there's a cost, because if you had the solution, then you could study from it and you could understand what you did wrong a little bit better. So I've asked the grader to give you some instructions in the comments on which problems you had mistakes and maybe an idea of what the issue is. And if from the grader's comments, if you still aren't exactly sure maybe what went wrong, I really would ask you please come see me in my office because I'll help you understand how it was supposed to be, and I'll let you look at the solution in my office because that way I know you won't be taking a picture or sending a PDF to the sophomores or anything. But yeah, there's costs and benefits, and that's just kind of where I landed because I want to be able to reuse some of these questions again in the future. So that's the why. Today we're going to be talking about pipe networks. So we've done the Hazen-Williams equation, the Manning equation, we've done the Darcy-Weisbach equation, and all of those were to find out how pipe friction could be estimated as water's flowing through a single pipeline. Now we're going to get a little more complex and wonder what happens when it's more than just a single pipe. Chase, will you put your phone away? Thank you. All right. So that's what we're doing today. And one of the methods, the Nodal method, allows us to handle problems when the water is flowing in parallel through multiple pipes. So you remember the Moody diagram. And the Moody diagram has a section to the right of this dashed line where the F value isn't changing as the Reynolds number changes. And that's the fully turbulent flow region. Now I've told you before from an equation standpoint what to do with the fully turbulent flow assumption, but this is kind of a graphical representation of when the F value isn't going up or down as the Reynolds number changes, that means it's only dependent on the relative roughness. And so there's some threshold limit above which any additional Reynolds number is having no more effect on the F value. So we take the Jane equation, and when we're invoking the fully turbulent flow assumption, we assume the Reynolds number is so big that F only depends on the relative roughness. Or in the Colebrook, it's the similar thing. The F value only depends on the relative roughness. That's the fully turbulent flow assumption, and I mention it because we're going to be using it over the next couple of class periods as a starting point for estimating the F, and then we'll have to go back and check it and adjust if necessary. But it's a good starting point when you don't yet know the velocity and you need to have some F value and a better F value than a random guess. All right, so here's the basic principle of the nodal method. It says take a junction of a pipe and look at the flow in versus the flow out. So this is a node where three pipes are coming together. And the continuity equation that we talked about in Chapter 5 in fluid mechanics, continuity is in equals out. That is, at the junction, there's no capacity for storage. It's just a fully enclosed pipe that's all welded up, and there's no storage there. It's just the water's flowing in, immediately goes out. And from a flow rate perspective, what we can say is that the flow through pipe Z is going to be the sum of the flows through X and Y in this junction illustration. So here is our control volume. You maybe remember in the Reynolds transport theorem talking about control surfaces and control volumes last semester, and what we did was we kept track of an accounting of the in versus the out. And we're going to use that same idea here in the nodal method. And the application for it is when flow diverges through a pipe where maybe we know the flow rate through a single pipe, but it then encounters some indeterminate path. And by the way, this is a top view, although it wouldn't matter if it was a side view. It would be the same basic idea that if the water encounters a split, what we want to know is how much of the flow will go through one pipe versus another pipe. It's all eventually going to come back together. You can see that here in the downstream pipe, it's back to its same known flow rate, assuming that we haven't done any withdrawals. There's no side pipes, there's no outlets. It's just an enclosed system that momentarily splits, and so we don't know how much goes through one pipe versus another. So let's talk about some of the factors that maybe would control how much goes through pipe C versus how much is going to go through pipe B. Any questions so far? What we know is that the amount of flow through B is how much there was in A minus the amount that's going through C. In other words, the sum of these two, B and C together, is QA. So if we want to know QB, we'd say it's QA minus QC. But initially, we don't know either C or B. So we can't solve the mystery until we know the flow through at least one of them. Let's think qualitatively, just in terms of the basic concepts. The idea is that it doesn't matter what route you get there, the energy loss is the same. And has anybody here ever been to Winter Place before? I just checked out their cameras today. It looks kind of, the warm weather's not so great in the ski industry, and so they've got more of the runs open than I would have guessed. But I actually really like Winter Place. So if you're here in the parking lot, it doesn't matter if you go on Woods Run and then some path, Snowfield, Cascade to get to the parking lot. It doesn't matter if you go that route or if you go on the green Easy Run, Ridge Runner, Buttermilk, and so on. The delta Z is the same. From the top of the mountain to the parking lot, the energy change is the same regardless of the flow path or the route that you take. One is certainly steeper than another, but from origin to destination, it doesn't matter what route you get, the delta Z is the same. So that same kind of idea, that's an analogy to what we're going to apply in this case. We're going to say that the amount of energy there is at this junction compared to the amount of energy at the downstream junction, it doesn't matter which pipe you go through, you're going to have the same head loss. Either if you go through pipe B or through pipe C. It's going to be the same amount of head loss. Okay, so let's consider what if both B and C had the same length and the same diameter and the same material type. So here is the Darcy-Weisbach equation, and it tells us the head loss as a function of friction factor, length, velocity, diameter. And the concept that I've just told you is that whether you go through pipe B or through pipe C, the head loss is the same. You can't have a different amount of head loss because they both come back together again. So if the head loss is the same through both pipes, and let's say the water's flowing through pipe A and now it encounters the split. If both of the paths are the same, what would you expect will be the case for the flows? How much goes through each of them? Huh? The same amount. That's exactly right. It's going to be a 50-50 split. There would be no reason for more flow to go through B than to go through C. So there's going to be an equal amount of flow through B and C if the pipes are identical. And so far in this first bullet point, what I'm telling you is the pipes are identical, so the flow rate's going to be identical. There has to be a reason for more of the flow to go through one pipe than is going through another pipe. All right, so what if they both have the same diameter and the same pipe length, but what if pipe B, this one on top, what if it was more rough? Then which pipe would you expect to have more flow versus less flow? Travis?
C.
You're saying, but which one, more or less? Pipe C would have more flow. He's right. How did he know that? Why is pipe C going to have more flow? There's less friction. So there's less resistance to the water going through it. Does that mean that pipe C, let's say pipe B is the rough one? Does that mean that there's going to be no flow through pipe B? I mean, it's going to have some. It's just going to have less. It's going to be whatever flow gives the same head loss through both route. And so if pipe B is really, really rough, like jagged, then the flow is going to have more resistance through that route. And so it would have a little bit of flow, but more of it would go through the easy path. So it would be whatever balance, whatever flow balance makes it so the head loss through both pipe directions, the head loss through pipe B and the head loss through pipe C are equal. So here's another what if. They have the same length, the same material, but pipe C is bigger. So what do we know about the relative flows? Jeffrey? Pipe C versus pipe B. Which one is going to have more water if pipe C is the big one?
I would say pipe C.
You're right.
Because it has more area, respectively.
Exactly. It has more area. And so the bigger the pipe, the easier the flow is through there, and so more flow will go through the easier path. Now here's a tricky one though. What if pipe B is bigger, but what if pipe C is shorter? And then to muddy the waters even further, what if pipe C is more rough? Okay, so this first statement would say pipe B has more flow because it's bigger. But then the second one, the shorter pipe would have more flow. So they're kind of at odds there. You know, you're going two different directions in which is the easier flow path. We don't know the relative magnitude until we actually substitute some values in. And so for this bullet point, we couldn't just say right off the bat which one is going to have more flow. We'd need to actually do some calculations on it. But what we do know is that the two head losses are equal. The head loss through pipe B is going to be equal to the head loss through pipe C, regardless of the length, the diameter, the friction factor. Just the water is naturally going to set itself up so that the head loss is equal. And the reason why is, let's think about pressure. If the pressure at this junction is 500 kPa, you couldn't lose 100 kPa through one pipe, so now you're 400, and then you couldn't lose like 200 kPa through another pipe because they both end at the same place. So it's not like you could have 400 kPa if you go through pipe B or 300 kPa through pipe C. Since they both terminate at the same location, there has to be the same pressure drop through either route. We can substitute the Darcy-Weisbach friction equation into this relationship, and this is what we get. And this is how we can find out the relative quantity of flow that goes through each pipe. Is there's going to be a known F, a known length, a diameter, and you can solve for a ratio of the velocities. In other words, just to restate it, it doesn't matter what route you take, route B or route C, the head loss between the 2 points is the same. You're losing the same amount of energy. So we can put that into the energy equation. And the way that you're used to seeing the energy equation is this. P1 divided by gamma plus Z1 plus V1 squared divided by 2G plus HP equals P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus HT for turbine plus HF, or head losses if we're including the local losses. So this is the energy equation as you're used to seeing it. And it's talking about flow through a pipeline where the direction is from 1 towards 2. So this is old news. But we could rearrange the energy equation in a way that will be kind of useful and advantageous for us when we're solving certain problems. And this is the energy equation when we've rearranged it slightly. So H, in this formula, we're talking about the total head. And so it means the pressure head, the elevation head, and the velocity head. So that is H1. And those three terms on the right-hand side of the equation is H2. So H2 equals H1 minus the losses. So minus the friction losses, minus the local losses. And here, remember, H sub F is FLV squared divided by D2G. Another way we could write that is FLQ squared divided by D2GA squared. So instead of V squared, we could say Q squared divided by A squared. Why would we do that? Well, sometimes we know the flow rate through a pipe, but we don't know the velocity because the diameter may not be given yet, or for other reasons. But what this is illustrating is that the energy equation can be solved where we're thinking of the total energy at this downstream location. So what we could say is the head at 2 is the head at 1 minus the losses plus however much energy is added by the pump, if there is a pump. And we're assuming here that there's no turbine, that the turbine term is not included in this expression of the energy equation. Now, so Q squared, you'll notice here they've done Q times the absolute value of Q. And the reason for that, instead of just squaring it, is that sometimes you make an assumption about the direction of flow, and it turns out to be wrong. And if you just square your flow rate term, then flow direction isn't accounted for. But if you keep it separately, like if you say flow clockwise is negative and flow counterclockwise is positive, then having one of these values be in an absolute value preserves the directionality of flow. So that's why we don't just square the Q and, down here it's divided by the absolute value of Q. The idea behind that is we'll get to a point where flow direction is important. And we want to, in this equation, we're going to use this one a lot, we want to preserve some sort of an indicator of the flow direction in addition to the flow magnitude. So here are all the same definitions and terms that you've seen before. But this is called the nodal method because you're comparing the energy at different nodes. At node 1, the total head, you're going to calculate it. At node 2, the head is however much energy there was at 1 minus the losses through the paths. Travis?
We're going to stick with the conventional clockwise and maybe counterclockwise.
Actually, we'll say clockwise is positive for flow rate when we're in the loop method. But in the nodal method, the direction doesn't come up in the nodal method, but I just want to introduce this form of the energy equation now because we'll use it both in the nodal method and in the next approach, which is called the loop method. But flow does go from 1 to 2, and the reason for distinguishing there is that losses are on one side of the equation, and so we put the losses on the same side of the equation that's downstream. Okay, so here is an example that can teach you the nodal method. The process that you'd follow, if we know that there's 3 cubic meters per second going through a pipe and we want to find out how much goes through B and how much goes through C. First of all, we'd find out what is the total head at 1. Then we'd find the head at 2 in terms of QB and the head at 2 in terms of QC. So that is, let me go back to it, this kind of a relationship, setting the two equal to each other, and then you can equate the flow rate through B in terms of the flow rate through C, and then use continuity to know, the relative amounts for each, so then once you apply continuity you can find the absolute amounts for each. And so then once you know the flow rates, you can substitute the Q's into this energy equation and find out how much head there is at 2, the downstream location. All right, that's awfully abstract, and so let's be specific. I think a specific example makes the process and the whole situation a lot more clear. Water's going through this pipeline, through A to B, we know it's 3 cubic meters per second, but then the flow splits. Part of the flow is going to go through route 2, and part of the flow is going to go through pipe 3. And what we'd like to know is how much flow goes through each of those pipes. What is Q2 and what is Q3? We have the data that describes the length of the pipe, its diameter, the material is known, so we have the equivalent roughness, and we're going to assume fully turbulent flow, and so here's the Jane equation having been modified to use the fully turbulent flow assumption. So how much flow goes through pipe 2 and how much flow goes through pipe 3? First of all, what you should do is calculate the F value. Let me write this on the board. And then I'm going to turn you loose to do some of these calculations because I think it's more meaningful if you run the numbers rather than just watching me do it. All right. So first thing you need to do is find F2 using the fully turbulent flow assumption. Find F3 using the fully turbulent flow assumption. And then set the F2 L2 V2 squared divided by D2 2G is equal to F3 L3 V3 squared divided by D3 2G. So use that to find V3 in terms of V2. Actually, let's find V2 in terms of V3. Yeah. All right. So basically, to substitute all of the known data into these two into this expression and find, like, what's the relationship between V1 and V2 once you found the F values. In the end, we want to know the flow rate through each pipe, the Q value.
Yeah, I just accidentally messed up the value. Like, the system was right, but the execution was not. If that makes sense. You waited for that? It's just brandy. Sounds like a bad plan.
That's right. So then the next thing to do is check, does it actually fully turbulent? So now that you have the Q value, you can get the Reynolds number and use the full J equation. How's it coming along?
I don't think I may get the same value as you. I get 1.5.
For which part?
V2. I think I could have just simplified it incorrectly.
So this is your substitution there?
Mm-hmm.
Yeah.
Is it?
It's 550 with the length.
Oh, yeah, I put the diameter on accident.
Oh, yeah.
That'll do it. Thank you.
So now that you've got that, what you can do is put it into the equation that's on the board in the box. That's Q, like Q2 plus Q3 together is 5. So you put that 1.204 in place of the V3.
Oh, okay.
You guys? Or B2.
There's so many places you can mess it up.
Okay, so on the screen I've got it solved through what are both of the velocities. We find the velocity 2 in terms of the velocity 3 and then substitute it into the continuity equation, which says that the flow rate through both of the pipes together should be 3 cubic meters per second. And so we put in the known area for each pipe, V3, and then instead of V2 we put in what is V2 in terms of V3, because now we've got one equation with only one unknown, and we can solve for what the magnitude of velocity 3 is, and so it should be 8.29 meters per second, and therefore that means the velocity through pipe 2 is 9.98 meters per second. And if we want the Q, then you'd multiply these velocities by the known areas for each pipe. So the areas are calculated for us, and so 0.1963 for pipe 2, 0.1257 for pipe 3. So there's the flow rate for pipe 2 and the flow rate for pipe 3. Okay, now remember, these are the flow rates through each pipe if the flow is fully turbulent. If the flow isn't fully turbulent, then the F values we've estimated are inaccurate, and there's going to be a slightly different balance of how much goes through each pipe. So anytime we invoke the fully turbulent flow assumption, we need to go back and check it to see if that's accurate. So need to check the validity of the fully turbulent flow assumption. So let's do that. Let's check it. And so if we put in the velocity for pipe 2 and the diameter for pipe 2, we can get the Reynolds number. You at this point can just observe. It may be a struggle to keep up with all of the calculations. I just want to show you that, you know, if you do check the assumption. Why is it turning blue? That's all right. If you check the calculate the Reynolds number through each pipe, and calculate what would be a new F value. So now this is the full Jane equation instead of just the fully turbulent flow. And so pipe 2 before, when we used fully turbulent flow, we got that our flow rate, the F value was supposed to be, really went too high. All right, so if you do use fully turbulent flow, 0.01493, or the updated 0.01498. So that's less than a 1% difference. So actually the conditions are fully turbulent. When we have this updated F value, if we wanted, we could substitute these new F values in here and solve for a slightly different velocity and a slightly different flow rate. But the difference is going to be less than 1% since the F values were within 1%. So that is how you figure out how much goes through each pipe. It's by, number one, knowing that you have the same amount of head loss through each route. And so that's where we set them equal to each other. That's the concept there. And then the other concept is that the flow rate through each of the pipes together is equal to the sum total of 3. So flow rate through pipe 2, flow rate pipe 3 is this 3 cubic meters per second. All right, so with our remaining time, I wanted to show you a little bit of information about this problem, which is on the homework assignment. It's really the same thing that you just solved, except for instead of 2 flow paths, there's 3 flow paths. So I give you, even on the handout, the assignment description, the PDF that's posted in Blackboard, all of these steps that you're seeing on the screen now, those are also on the file for the homework assignment. I step you through what you need to do for each of the pipes, starting with a guess value of F. Then you find the relative flow rates, all in terms of one of the pipes. And then you combine them together. So the flow through the 3 pipes together is just going to be the total. And then you need to check the assumption of fully turbulent flow and update if it's not within 1%. If the new F value isn't, if it's more than 1% different than the original guess, then you'd need to repeat the equation over again. Repeat the process with the updated F values. So we're taking, instead of 2 flow paths, it turns into 3 flow paths for the homework assignment. That's one of the problems. And the other problem, let me just pull that up real quick. All right, this is the other problem. So you need to apply the Nodal method. There's these tanks that are connected at pipe A, at location A, since there's a tank there, we know how much head there is at A. And this tank is connected at B, so that defines the total amount of energy that there is at B. And what we're trying to figure out is how much flow is going through each of the pipes. And so I've given you some pretty lengthy suggestions on how to solve this problem, some tips here, and you can set it up on the spreadsheet using a method that we'll talk about in class on Friday. But I make it really clear here that this is a nodal method problem. I underline, caps, tell you that this is not a Hardy cross problem. We're going to start in on the Hardy cross method on Friday, and I wanted to emphasize right now, since we've just talked about the nodal method, that this problem can be solved with the nodal method, and you shouldn't use the Hardy cross method on it. And so the idea is you don't know of this 0.2 that comes in at C. You don't know how much of it goes through pipe AC, and you don't know how much of it goes through pipe BC, but you do know AC plus BC equals 0.2 cubic meters per second. So you apply the nodal method at this junction, and then you do the same thing at junction D. You know that QDC, DA, and the flow rate through pipe dB, that those two flow rates together equal 0.2 cubic meters per second. So you're applying the nodal method at junction C and at junction D, and then you'll be able to figure out how much flow is going through each of the pipes. And so we'll talk more about this on Friday, but just in case you get an early start on the assignment, I wanted to point out that this problem 2 is a nodal method problem and not the Hardy cross method, which will start on Friday. All right, so that's all I've got for you today. I'll see you in class on Friday.